Good morning, my dear students. In the last module, we had considered the vector nature of velocity and how to deal with the problems of velocity both in magnitude and direction. In the present module, we will now see on the same lines about acceleration. Acceleration also is a vector quantity, So this vector quantity has a magnitude and direction, and we should know what is the effect of this vector quantity on the velocity, because the velocity is affected by acceleration. The acceleration vector affects the velocity vector. Whenever there is a change in velocity taking place, we say there is acceleration there. In other words, because there is acceleration, there is change in velocity taking place. But we define it in different way generally. The rate of change of velocity is acceleration. We define like this. That means if you know how the velocity is changing, then we will be able to understand what is the acceleration. In fact, the story is otherwise. What the acceleration is, how the acceleration is, will result in how the change in velocity is going to take place. Therefore, the understanding of the velocity from the acceleration becomes important. So let us now see here in this case, in coordination with the definition of acceleration what we have given, how to deal with this vector quantity called acceleration vector. We will start with a simple case when a body is traveling along a straight line. Suppose the velocity is v1 initially, then the velocity has become v2 in the same direction. That means only the speed of the body is changing, the direction is the same. So at some t is equal to t1, the velocity is v1. At t is equal to t2, the velocity is v2. Then what we understand is this acceleration must be taking place along the same direction itself. That's what we have to guess from this first, because if the acceleration was there in some other direction, the velocity will not be along this straight line. Suppose now you want to find out the change in velocity and hence the acceleration. We can write the change in velocity in this case is v2 minus v1, and time taken for this is t2 minus t1. So by definition of acceleration, we can write this as v2 minus v1 by t2 minus t1. This you can understand. This is equal to change in velocity by the time taken. This is the average acceleration, because this is over a period you have taken. What you get is an average acceleration here. Well, but if you see this situation, though we have put the vector difference here v2 minus v1, the vector difference here is simply the scalar difference itself, v2 minus v1, because it is in the same direction. As far as the direction is concerned, there is no change. So only magnitude of the velocity, that means the speed is changing. So acceleration will be having the same direction as the change in velocity. Suppose v2 is greater than v1 in this case in magnitude, then what we understand is this v2 minus v1, the delta v will be positive. That means it will have the same direction as v2 in the same direction. This is positive direction. That means the acceleration is given by delta v by delta t. This is put there as that, v2 minus v1 delta v, and it is in the same direction as v2. That is what we conclude from the definition of acceleration here. Suppose the value of v2 in speed, the value of the v2 is less than v1, suppose. The body is moving along the straight line itself, but v2 on the other hand is less than v1, suppose. then what happens? This change in velocity, what you have written as v2 minus v1, becomes negative. It is in the direction. This is smaller, this is larger. Minus indicates the velocity is, the speed is decreasing there. Change is with a minus sign creating decrease in speed. So in this case, the acceleration is given as delta y by delta t with a minus sign. So average acceleration takes place in the opposite direction as v1 and v2. v1 and v1 in this direction now. And v2 may be in the same direction. The magnitude is less. That means acceleration must be in the opposite direction. That is what is shown by minus sign. Negative direction is this one. That means the acceleration is here, reducing the velocity. Speed is decreased. It is working as retardation or deceleration, what we say. So if it is moving along one line like this, by the magnitude of this being either plus or minus, accordingly we can decide whether it is the change in velocity is going to be due to acceleration or due to retardation, we can say. But in general, because they are vector quantities, suppose the velocities are in any other directions, then how to go about it? Suppose now you have the initial velocity in this direction and some final velocity is in this direction. Suppose this is v1, this is v2. Put in the vector diagram here. The body is going like this, and out sometime it is found to be going like that. Put on the vector diagram to get what is acceleration. Now we want change in velocity. We want difference like what we have got here. We want v2 minus v1. That is going to be the change in velocity. By definition, final velocity minus initial velocity. That means this v2 will be equal to v1 plus delta v. That is v1 plus change in velocity. Like velocity is a vector quantity, initial velocity has a particular magnitude and direction. The change in velocity also will have a magnitude and direction now. Together, when you put like this, you will get the final velocity v2 there. So if you see in the vector diagram here, if this is v1, that is v2, this is final velocity, this is initial velocity. By triangle law, you will be able to get the final velocity v2 as the sum of v1 plus the delta v. So the delta v must be in this direction. So what is delta v? It is change in velocity. So when you consider the acceleration now, average acceleration like what you said earlier, it is v2 minus v1 by t2 minus t1. This is what we have written as delta v by delta t. What will be the direction of this acceleration now? This is a vector quantity. So the direction will be, see here, in this figure, in this equation, delta v is the vector. Time is not a vector. So it will have the same direction as change in velocity. So this will be the direction for the acceleration also. It will be direct. This will be direction. So initial velocity, final velocity. So always acceleration will have the direction of change in velocity. So the change in velocity is whatever direction it is, we can always obtain it with the help of the triangle law of addition of vectors, like what we have shown on the figure. So initial velocity plus change in velocity gives you final velocity there. So this is the principle of understanding the direction of acceleration. Whenever your body is moving, if the velocity is changing, you want to find what acceleration is, put the vector diagram for initial velocity and final velocity, find out actually change in velocity from the vector diagram, and that will be the direction of the acceleration. Once you know the magnitude of that value, that vector, you can find out the value of the acceleration also in magnitude. So this is the principle of understanding the acceleration vector. Let us see an example further. Suppose you have a body moving along a curve like this. It is starting from this point P1, say another point P2, it is going like that, and it is moving like this. Initially the velocity will be along the tangent. Always, whenever a body is moving with a velocity, its velocity at that point will be along the tangent, whether it is a curve or a straight line. For a straight line, the tangent will be the same as the straight line. So here it is along the tangent. Then after some time, this P2 can be any point in general. From point to point, it is now, I can call this is P3, and say P2 here. The direction will be like this. That will be the velocity at that point P2. I will call it as say V2. So P2 is the point where the velocity is becoming V2. P1 is the point where it is V1, and therefore there is a change in coming up here. This change in velocity is because of acceleration. There must be some acceleration taking place. That must have a direction, that must have a magnitude. Suppose we consider this as a circular one or any curve in general. Then we can represent it here. Suppose you draw the vector diagram here separated to show it. That is the final initial velocity. The final velocity is just like what I had drawn parallel to this one. Suppose this V2. This will be change in velocity now. That is delta V. That is nothing but V2 minus V1. So what is the direction of that one? It is, you can see, it is, here it is too far away, but you take points very close by. The direction of change in velocity, if you draw the figure here itself, vector here itself, it will be something like that. But if the point P2 is closer to P1, that means both velocities are almost drawn at the same point, that will miss the next point only. You can see that will be inward, it will be inside the curve like this, it will be inside the curvature like that. So that is the direction in which the acceleration will be. So when a body is moving along the circumference of a curve like that, when the velocity is changing from moment to moment like that, both in magnitude and direction, the acceleration is always directed in the side like that. So that is what this one is. So in that case, we can get the acceleration once again, the average acceleration in a given time as V2 minus V1 by T2 minus T1, like delta V by delta T. Once again, the average acceleration because you take finite points P1 and P2 at a finite distance rather. Suppose these 2 points are very close by. That means P2 is very close to P1. The time interval will be practically 0. The delta T will be tending to 0. In that case, in this limitation, you will find the average acceleration equation will be coming into as instantaneous acceleration at P1. So instantaneous acceleration, if you take A, we will write the same thing as limit of this delta T tending to 0 as delta V by delta T is evaluated. We will write the same thing as dV by dt in the notation of calculus in derivatives there. So that is how we get the acceleration in the case. So what is said is, if you know the velocities, initial and final velocities, you must draw the vector diagram, and from that you must get delta V, the change in velocity, and hence obtain the acceleration from there. Then the acceleration being a vector quantity, it can have components. We can represent the acceleration in terms of the components also once again. So coming to that understanding here, we can represent the acceleration vector in 3 components: ax I, ay j plus az k. What does this mean? I, j, k, are the components, unit vectors along the x, y, z directions. Therefore, ax becomes the x component of or I component of the acceleration vector. Similarly, this is the j component of the acceleration vector, and that is the k component there. So these three components, we can also represent the vector a here in terms of the components like this. Then, if you refer to the change in velocity, we have said that acceleration is dx by dt, so dv by dt, rate of change of velocity, as we put in terms of calculus there. This is coming there, and we represent this here. Acceleration in three components means this vector v, or the change in velocity that is coming up, also can have three components, like what I have been showing just now. If you draw the initial velocity here and final velocity there, if you have a change in velocity put in this direction, it's a vector quantity. This can again have three components. This can be analyzed in three directions: x direction, y direction, and z direction, like that. Accordingly, three components will be there. That means for change in velocity also there will be three components, and that is represented here in the derivatives like this as d by dt of those three components. That means each component here, each velocity also here, v1 and v2 also are vectors. Therefore, they also have got three components. So when v1 changes to v2, the x component may be changing, the y component may be changing, or z component may be changing, or all the three may be changing. Therefore, in the derivative when you put, we write the velocity in terms of the components there. Suppose the velocity is in terms of these components, then we can write it as vxi, vyj plus vzk. This means we are differentiating the velocity vector in terms of its components now, which means you can separately differentiate the values dvx by dt in the direction of y, similarly dvy by dt in the direction of j, dvz by dt in the direction of k. So this is how we get the components of the component representation of the vector. That means this gives you the change in the velocity in the x direction, change in the y component here, similarly change in the z component here. This is the way of understanding the acceleration vector in terms of the velocity vector there in turn. We had also mentioned in the last module that when the velocity vector is to be understood, you must understand the position as a vector in terms of the position vector. So changes in position vector will give rise to velocity vector and its components. Similarly, changes in velocity will give rise to the changes in the acceleration components, and hence we represent these things. That means if you know the change in position from point to point given in the vector direction as position vector directions, then you will be able to work out velocity and as well as acceleration components in the direction. We shall take a small example now. Suppose the a particle is moving such that its displacement or the position is changing according to the equations given. That means its x position, y position, x coordinate, y coordinate are changing according to the equations given here. 2 plus t square plus t, and this is t cube plus t square. So this is the variation. T is the time, that means with the time it is changing like that. In which case we are asked to find out the acceleration components ax, ay, az instantaneously and how it varies. We can find out that. Once you find out the acceleration components at any in general variation, you can always find out the average acceleration or acceleration at any given time also. See, for example, if you now find out dx by dt, it gives you the change in the x component of the velocity there. It gives the change in the position vector along the x direction. That means it gives the velocity vector there in that direction. That means x component of velocity vector. Similarly, if you write dy by dt, you will get the j component. So together it gives you the velocity vector now. So now you can differentiate this and write here. If you differentiate this with respect to time, you will get the answer like this, because this is 2, differentiation of 2 is constant, because therefore it is 0. Next term, differentiation is 2t. I think you remember the formula for differentiation what we gave in the last module, and this is 2t plus 1, because differentiation of t is 1 with respect to time, and this is I. This is I. So this similarly for y it is 3t square plus 2t into j. So this is the velocity vector what we have. Suppose you want to find out this, that is the way, this is how the velocity vector is changing with the time. X component changes like this, y component changes like that. Now suppose you are asked to find out the acceleration, variation of acceleration. You have to find dvx by dt. That means differentiate this once again with reference to time. Then you will get 2I, because this is differentiated 2 into 1, this is differentiated with 0, so I plus 6t plus 2 into j. The differentiation for the y component here. So this becomes the acceleration vector. Variation now. Variation of acceleration with time. The vector is this. Now once you know this, you can find out either instantaneous acceleration or you can find out average acceleration also. For example, suppose you want to find out the acceleration at 0, t is equal to 0. It becomes instantaneous acceleration at t is equal to 0. See what happens here. Put t is equal to 0 in this equation. See what we get here. You will get this is 0, this is 2i, the 2 here, 2i plus 2j will come there. Similarly, you want to find out the acceleration at t is equal to 5. Say, for example, 5 seconds. So then you get here 2i, there is no variation here with the x-axis, therefore it is 2i plus, this becomes 6 into 5, 30 plus 2. So it becomes 32j. So this is at t is equal to 0, this is at t is equal to 5, that's how the acceleration is changing. Acceleration is not a constant now. These are instantaneous accelerations at that moment now. You want to find out average acceleration now from t is equal to 0 to t is equal to 5, say. Average acceleration you want. How do you get? You can find the average of these two and put it there. You can do like that. That is average of x components, that is 2i plus 2i by 2. So that is 2i. Here it is 32 plus 2 is 34. 34 by 2 is 17. 17j. So this becomes average acceleration at that time. You can also find out the average acceleration from velocity also. So you can find out from average velocity change and then find out. Anyway you can find out. Once you understand how to work with the concept of the acceleration vector, you can start from velocity and find out, or you can start from directly from the acceleration equation and find out like that also. That is what is meant by the understanding of the acceleration vector. Suppose you want to find out this is the average vector, acceleration vector. So we want to find out the average acceleration magnitude alone, suppose you want to find. That means you have to put the square of this and the square of that and then work out. That will be the acceleration magnitude, average acceleration magnitude. You want to find direction. If this is x, the acceleration direction is like that. This is x-axis. This is y-axis. Suppose this j direction, the acceleration direction. Then this angle is given as alpha. Then alpha is given by tan inverse. You can see that this is ax component in the ay component here, aj ai component here. So it is ai by aj. That means ax by aj, or you can write ax also. You can write ax. Y component by this y component by x component. That means tan inverse 17 by 2. So you can find out this tan inverse 8.5 from the tables and find out the value where it is taking place. So like that we will be able to get magnitude and direction once you know the vector separately. You can attempt such problems given like that in that. That is one aspect of it. There is another aspect of this components of acceleration. We have put this acceleration vector now in general with x-axis and y-axis. That means j direction, that is I direction here. That's what it implies. There is acceleration we said. These are general directions, always x direction, y direction, like that. But acceleration vector is always having an influence on the velocity vector. Because there is acceleration, velocity vector is changing. Like for example, suppose the velocity vector is in the direction like that. This is velocity, suppose. There is some acceleration taking place in some direction like that, say. That is acceleration direction. So this is initial velocity, maybe this. Or suppose we have velocity direction like this, and we can have the acceleration anywhere taking place in some general direction like that, suppose. It is acting like that, suppose. That means there is some angle between the velocity and acceleration. Unlike the general case, what we say, in the particular case what I said, when acceleration and velocity are in the same direction, what happens? The velocity will change only in magnitude. Direction will continue to be the same. So acceleration will be in the same direction, say. Now, this acceleration can be resolved into three components. X, Y, Z components, like what we said. X, Y, Z components can be there. But the component, as what is shown here, that component which is responsible for changing the magnitude of the velocity, that is only the speed of the velocity, is a different component. It is not this X component or Y component. It can be a different component. That means, if this vector is resolved into two components, one along the direction of the velocity, one perpendicular to that one, see what difference we get here. Let us see what matters. We take this angle as theta, suppose now, and we have one component here in this direction. We call it as a parallel component. You know, that is a parallel component is a cos theta. Similarly, the other component will be at right angles to this one. This is a perpendicular, I call it. This will be a perpendicular component, I call it. This is a sin theta. What is the advantage in doing like this? That's what we will see now. You can resolve the component, the vector A, that is acceleration vector, in two directions which are mutually perpendicular. One parallel to the velocity, another one perpendicular to the velocity. By doing so, what happens is, we can understand one thing very clearly here. This component of acceleration, that is a parallel component, that alone affects the velocity in magnitude. This component will not affect the magnitude there. Why? This vector, which is right angles to that V1, can have no component in that direction, can have no influence on that vector there. So, a parallel component will create the change in velocity, delta V. That will be there. So, that's why we get this one. So, instantaneously what you are getting as dV by dt, which is a scalar thing I am telling you, is because of the parallel component. Just like what I said, velocity in the same direction, acceleration in the same direction. So, V1, V2 in the same direction, both are the same magnitude. So, acceleration also will be in the same direction, that is the direction of change in velocity. That principle is applied here. So, this component of acceleration, which is parallel to velocity, will therefore affect only the magnitude of this velocity. So, the change in velocity comes in magnitude only parallel to that one. Take this component. What is this is doing? What is the influence of this one? This component is not changing the magnitude. Then what is it doing? It is changing the direction of the velocity. See the picture here. This is change in velocity vector. This is initial velocity. So, final velocity will be, this is what is happening at the point where it is moving. To show them how the direction of the change in velocity is, put a separate diagram here to show that what the influence of that is. The velocity is initially like this, V1. Change in velocity is in this direction. This is V1. This is acceleration change in velocity, that is delta V. So this happens to be the final velocity. Now you can see in the picture here, the initial velocity is this, change in velocity is this, that is the change direction of the acceleration, final velocity in this direction. So final velocity will be something different. You can see that. If it is like that, the magnitude of the velocity is produced by the component parallel to the velocity, and this change in direction coming up here is because of the influence of this particular one. So therefore, this component will try to pull the velocity like this, whereas the magnitude to which extent it must be pulled will be shown by that parallel component here as happening there. So either the magnitude may be changing or direction may be changing, both may be changing sometimes. Like for example, suppose a body is moving along a curve like this. This is some general curve. So in going from here to there, direction, magnitude is changing, direction also is changing. So change in direction is brought about by a component like this. That component is perpendicular to the velocity here. The change in magnitude coming up here is given by a component that is parallel to the velocity there. So like this it will happen. Suppose the change in velocity is taking place only in magnitude and direction is not changing. Then, like what I said in the beginning, it goes along a straight line. No change in direction, only change in magnitude. It goes along a straight line. If there is change in magnitude and direction both, then it will go on a curve like this, a general curve. On the other hand, suppose you take a smooth curve. A smooth curve like this. A curve which is a part of circle. And is going with constant speed, suppose. So there is no change in magnitude, velocity here, velocity any other place is the same in value, but direction is different. This is different because direction has changed now. When direction has changed, the direction change has come because of the acceleration that is taking place inward, inside the concaveness of the curve there. So that is what the nature of the acceleration vector is. Therefore, it is often useful and it is very important also to calculate the change in the magnitude of the velocity and change because of the direction of the velocity there. So this therefore can be done by resolving the acceleration vector in two mutually perpendicular components usefully. One has parallel component to velocity and there is perpendicular component to the velocity. So that is what you must understand. So resolution is this, can be done anyway. Sometimes it is useful, sometimes that is useful, Isaac components, then you will get the change in velocity accordingly in those components. If you are doing like this, you are going to get change in velocity in the parallel component in magnitude. Direction is given by this one. If you put in the Isaac components, you will get the change in magnitude and direction there in terms of the x, y, z directions there. That's what you understand about the acceleration vector. On the basis of what I said now, you can now try to attempt problems from your modules given there and try to get into the grip of this following acceleration vector very well. We shall take up a small example and show it in figure here, in figures here, to understand this better. Suppose a body is moving along a direction with a velocity v1 equal to some 20 meters per second, and an acceleration is taking place at an angle of 60 degrees here, which is 4 meters per second square, say. Then what are the parallel and perpendicular components of this acceleration and what is the influence of those acceleration, we will see now. This can be resolved in two components as a parallel component, that is along the velocity, that is a parallel component, that is a cos 60, and a perpendicular component is there, that is a sin 60. Automatically it comes like that. So there is one component like that, one component like this. This is a perpendicular. Now what is the value? A cos 60 is 4, cos 60 is half, so it is 2 meters per second square. A perpendicular, this component is 4, sin 60 is root 3 by 2, that is 2 root 3 meter per second square. So a parallel component is changing the magnitude, a perpendicular component is changing the direction now. So what is change in magnitude of the velocity now? Change in velocity, that is change in speed rather we call it. It is given by this value. Suppose in after t seconds, after some 2 seconds say, initial velocity plus acceleration component into time taken. So this initial velocity value is 20 meters per second plus this is 2 meters per second square after 2 seconds, it is 4, a into t is 4, so it is 24 meters per second. So 2 seconds the velocity has become 24 meters per second along the direction of movement there. Change in direction has come. So change in direction is because of in direction. That is giving, this is one component. This is giving rise to the velocity parallel component. Velocity component parallel to the direction of movement there. Then in the initial velocity. This what will happen next one? The initial velocity in the direction is, if you take this perpendicular component, you want to find out that change in the velocity perpendicular to the acceleration, perpendicular to the direction of motion, perpendicular direction of motion. So this is this. Initially the velocity in this direction, there is no component here at all, so this will be 0, plus this is 2 root 3 into 2, that means 4 root 3 meters per second is the change in velocity perpendicular to the direction of that. So we want to find out net change velocity vector now. It is 24 some direction I into that direction, this direction I call as I suppose now, then plus 4 root 3 j, that will be the velocity vector after 2 seconds. That means this is in this direction, this is I direction I have given, so naturally this becomes j direction I have taken here, so I j directions are there, so components are like that. That way you will get the velocity. You want to find out what is the net change in velocity, net velocity v2 magnitude, then you must take this 24 square plus 16 into 3 also there, squaring this also. So that's what you have to calculate. So like that we will be able to get this. So this comes here as 576 plus 48, and you can add up and find out the final value. It is square root of 624, so many meters per second. So like this we can find out the change in velocity as a whole. Is a magnitude change. In which direction is the change taking place here? Directional change. Once again I gave you the change in direction is given by that alpha, which is tan inverse 4 root 3 by 24, y component by x component. That means there is equal to, alpha is equal to tan inverse root 3 by 6. You can still simplify, find out the value of root 3 by 6 from the tables and then get the value of alpha, where alpha is the angle of that final velocity with reference to I axis. This is I direction. So the direction of I, where will be that taking place, is given by this one. So I is like this. Suppose you will get some angle, you will get like that. So V2, this is I direction, that angle is alpha given there. So like that you will be able to get the answer for the magnitude and direction of the velocity finally, even though you can get the magnitude separately and direction influence separately from the acceleration components like this. That's what you can see. Some more examples are there. You can always try them. Thank you.